Hello friends, welcome back to this series where we go through and explain the book on quantum mechanics by Weinberg. Today, let's talk about something interesting. If you have been following this video series, you'll remember that we have discussed in details in lecture 21 how two angular momenta could be added together to form a composite system, which itself could be an angular momentum state. And we ended up deriving the possible range of angular momenta, as well as the associated eigenstates that could arise in such a union. Also recall that in lecture 20, we have shown that in a quantum system, the possible values of angular momentum measured along any axis can only take either integer or half-integer values. Taken together, this suggests that it may be possible for us to construct any arbitrary spin state in terms of multiple copies of spin halves. A standard example of a spin half system is just the electron. Note that we are not suggesting that any particle can be composed from electrons, but rather, if we understood how an electron transforms under rotations, we can then figure out how a particle of any spin transforms by looking at multiple copies of this simplest spin-half object. As we shall see, these multiple copies have a natural description in terms of objects with multiple indices, which are called tensors. This is the tensor representation of the rotation group. But before we go into all that, let's review what we know about the representations of rotations. A representation of rotations consists of two parts. The part being rotated, that in the context of quantum mechanics means quantum states, which are vectors in Hilbert space, and the part doing the rotating, operators that live in the same space. These are unitary operators that take in the rotation matrix R as parameters. R rotates the familiar 3D vectors around the direction and by the magnitude specified by the rotation vector. This rotation operator is generated by the total angular momentum of the system under consideration. The matrix R tells us how to construct U, since the different rotations must be combined in a specific way that is characteristic of rotations and must be reproduced by U. These rules of composition are encoded in the commutators of the angular momentum operators. We have discussed all these in details in lecture 19. The link to this video is in the description. Let's see how this rotates quantum states. Suppose we have a vector space sigma, which can be spanned by the basis states n. The condition that must be imposed on sigma is that any state in sigma can only be rotated to another state that lives in it. Only in this way can we completely describe all the rotations of the states in sigma. Think of it this way. Suppose we only consider vectors that live on a 2D plane. It would be impossible for us to adequately describe all 3D rotations, since these vectors might then be rotated out of the plane. Furthermore, sigma is an irreducible representation if it does not contain a smaller representation within it, meaning it cannot contain any subspace sigma bar that is itself a representation of rotation. In other words, an irreducible representation is one that does not contain a smaller representation. Note that although we are only talking about rotations in this video, the same concepts apply to other symmetries, for example, Lorentz transformations for relativistic systems. A simple example of an irreducible representation of rotations are the angular momentum states of the j-multiplet. Note that two multiplets with different quantum number j must necessarily be two different representations of rotation. This means, however we rotate a state in j, it will always have zero overlap with any state in j'. This is apparent by the fact that the square of angular momentum, j square, is invariant under rotations and commutes with u. Therefore, states with quantum number j cannot be rotated into states with a different quantum number j prime. So the only non-zero matrix elements of U can only be between two states from the same angular momentum multiplet. This means all the states from the same multiplet form a representation of rotation. But is this irreducible? The answer is yes, and we can prove this by showing that a rotation can always be found that links any two states within the multiplet. Let's tackle the non-trivial case where m prime is not equal to m. For example, m prime equals m plus some integer. Let's find a rotation such that this matrix element is non-zero. We can try a rotation around the x-axis. As long as we don't choose a z-axis rotation, since this would just become a phase when applied to the state Jm. And the inner product between m plus n and m will give 0, which is not what we want. Let's expand this exponential in a power series. We shall assume the angle phi to be small, such that higher order terms may be neglected. Recall the definition of the ladder operators for angular momentum along the z-axis. We can invert this and express j1 in terms of j plus and j minus, and substitute this into our expansion to evaluate the matrix element above. It is not difficult to see that the smallest power of j1 that would contribute to a non-zero value of the matrix element is just n, since this is precisely the difference in angular momentum that separates the two states. And furthermore, this term is the leading contribution as the angle phi is small. If n is positive, j plus in j1 will raise m by the required number, while if n is negative, j minus will do the job. And we can see clearly from this leading contribution that the matrix element is non-zero. Although higher order terms may also be non-zero, but for small phi, they cannot interfere with this result. Hence, we have shown that given any two states in the j-multiplet, we can always find a rotation that connects them. This means the j-multiplet is an irreducible representation of rotations. But why do we care about such representations? The answer is that they will tell us what are elementary particles. The key idea is this: the same particle can come to us with its spin pointing in various different directions, but nevertheless, we would still identify it as the same type of particle. For example, the spin of an electron can point in different directions, but it remains as an electron. Therefore, all these different spin states that can rotate into each other have to be associated with the same particle, whereas different irreducible representations can rotate independently. Therefore, it makes sense to associate them with separate particles. Note that what constitutes as an elementary particle is subjected to the energies of our experiments. At low energies, a hydrogen atom could be considered an elementary particle, while at higher energies, we may have to view them as an electron and a proton. And at even higher energies, like in a particle accelerator, even the proton has to be viewed as a collection of quarks. A simple example will make this clear. Let's just consider particles on the xy plane being observed by two different reference frames that are rotated with respect to each other by an angle phi. Let's also assume that these particles each carries some kind of intrinsic 2D vector, the vector v for one particle and u for the other. These vectors are given in the unprimed reference frame. How they are viewed in the prime frame is obtained just by applying the 2D rotation matrix which connects the two reference frames. We could try and group these two particles together as some kind of composite particle. The two component v and u vectors could then form one big 4-component vector, which is an intrinsic property of our composite particle. This large vector will also rotate in a well-defined way and thus form a representation of rotations. But notice that this 4-component vector doesn't really rotate as a whole, but rather its rotation matrix could be separated into two independent blocks that each rotates two components without any mixing between them. This is how we know a particle is not elementary, because given a suitable basis, it contains different components that can rotate independently from each other. In our case, this is obvious, but we could imagine a different choice of bases such that this block diagonal form is not so clear, and the 4 components would seem to mix with each other and rotates like a single object. On the other hand, if we try to view one of the particles as two separate particles, each carrying one component of the original vector, these variables can no longer be treated as intrinsic properties of two separate particles that can rotate in a well-defined way. They are each an incomplete representation of 2D rotations. We are forced to combine them in order to complete the representation. This is what we mean by an irreducible representation. Let's get back to the general representation of rotations. Consider a generic state psi that lives in sigma. How would this rotate? We can express this rotated state in terms of the basis n by applying the identity operator. And also, to put the components of psi in the same basis explicitly, we insert another identity. It is clear from this expression that we can cast the action of rotation in terms of the matrix U acting on the components of psi in the basis of n. This gives us the rotated components psi prime. Note that from here on, we shall use the Einstein's convention where repeated indices are automatically summed over, so that we don't have to keep writing summation symbols. We can now describe the rotations of any state in sigma by the rotations of its components in the basis n. These single-index objects, psi n, rotates like a vector under the action of the matrix U. If we take multiple copies of the basis, like n copies, we can construct something like a multi-particle state with components that have n indices. These multi-index psi will then rotate like a tensor. And here's how tensors rotate. Each copy of the state n in the product will rotate independently the usual way by the operator U. We can again insert the single particle identity operator after each U. Here, it will be convenient to use the Einstein's convention. This puts everything back into the basis n, and we now have one matrix U with each copy. We see that each index of psi simply rotates like a vector. This is how a multi-index tensor rotates. Now we are in the position to demonstrate what is advertised in the title of this video. That is, how to construct various irreducible spin representations of rotation out of copies of spin-half states. To simplify notations, we shall denote the two spin orientations by spin up and spin down along the z-axis by the usual convention. These two states will now be our basis n. But note that we are not suggesting that any spin could actually be composed of spin-half particles, but merely the way any spin state rotates can be perfectly simulated by a collection of spin-halves. They are indistinguishable just from their rotation properties. So to carry on with this project, we have better remind ourselves how spin-half states rotate. To calculate the matrices that rotate spin-half components, we will need the matrices of angular momentum J. The rows and columns of these 2x2 matrices are indexed according to this convention. These are just h bar over 2 times the Pauli matrices. We have covered these in lecture 20. See the link to the video in the description. The states corresponding to spin up and spin down along the z-axis are given by these columns. Therefore, the rotation matrix for spin half is given by, where we have plugged in the expression for J. Let's take a look at the determinant of this 2x2 matrix. The simplest way to do this is in the basis of the eigenstates of the Hermitian generator in the exponent. Lambda m is the eigenvalues associated with the eigenstates m. In this basis, the matrix U is simply diagonal, with the diagonal elements being just e to the power of minus I over 2 times the associated eigenvalues, which is just the eigenvalues of U itself. Since the determinant of a matrix is independent of the basis we choose to calculate it in, the determinant of U is just the product of its eigenvalues. This translates into the sum of the eigenvalues lambda in the exponent. Since the trace of an operator is equal to the sum of its eigenvalues, we can express this as the trace of the Hermitian generator. This is equal to the dot product between the vector phi and the trace of the Pauli matrices. We claim that the trace of the Pauli matrices is 0, which means the determinant of U is 1. We can verify this claim by taking the trace of the Pauli matrices directly, but there is a more general way that is both simple and instructive. Since the Pauli matrices are just proportional to the angular momentum J, and these have to satisfy the rotation algebra, we can calculate the trace of J just by taking the trace on both sides of these equations. Notice that the trace of the commutator of any two operators has to be 0 due to the anti-symmetry of commutators and also the cyclic property of the trace. This means the trace of the left-hand side of these equations must all be 0. And thus our claim is proven. We can check this directly with the Pauli matrices. Also notice that if we take the dot product of any real vector phi with the Pauli matrices, we get the most general 2x2 Hermitian matrix that is traceless. And since any unitary matrix can be generated by a Hermitian matrix, and those with determinant 1 can only be generated by a matrix that is traceless, this means the expression for U above covers all 2x2 unitary matrices with determinant 1. This is a rather important result in quantum mechanics, which will be revisited again and again. Such matrices belong to the group SU2. U2 are 2x2 unitary matrices, and S, for special, This means they have determinant 1. We say that a homomorphism exists between the groups SU2 and SO3 because elements of both groups combine in the same way rotations combine. SU2 represents rotations in the 2D space of spin-half states, while SO3 are 3x3 orthogonal matrices with also determinant 1. We have introduced these in lecture 19. They represent rotations in the familiar 3D real space of everyday life. This is where we get our intuition for rotations and distill out its essential properties, so that we could generalize this symmetry to more abstract spaces like the space of spin-half states. Both groups represent 3D rotations. 3D in this case means the 3 ways we could rotate an object around the 3 axes. In other words, all such rotations are generated by only 3 generators. Naturally, the next question we may ask is, what about more complicated rotations in higher dimensions, for example, d dimensions? These are described by SOD. Similarly, we may also want to compare them with SUN, as we did before for lower dimensions, but this time in a larger n-dimensional state space. Can these two represent rotations? To make a systematic comparison between these two groups of matrices, we can compare their numbers of degrees of freedom. The most straightforward way to do this is to count the number of real variables needed to describe these matrices. Let's start with SUN. These are n by n unitary matrices, and therefore must necessarily be generated by some Hermitian operator, A. This is required by the unitary condition. At the same time, the determinant must be 1, therefore A must be traceless. These conditions suggest that we could just count the number of degrees of freedom of A, which is the number of real parameters in a Hermitian, traceless, n by n matrix that has complex elements. The Hermitian condition says that an off-diagonal matrix element is related to another across the diagonal by a complex conjugation, while the diagonal elements are real. First off, n by n complex numbers equals n squared times 2 real parameters. But not quite. Since the diagonal elements are real, we have to multiply by half to correct for this. And for the off-diagonal elements, we also have to multiply by half, since they are not independent due to the Hermitian condition. So overall, we have to multiply this by half. Then subtract by 1 for the traceless condition. So the number of degrees of freedom for A is n squared minus 1. This is the number of generators of SUN. Now for SOD. For better comparison, let's also express this in the exponential form with generator B. But since this generates orthogonal matrices, it is an anti-symmetric matrix. Again, because the determinant of the matrices it generates is 1, B is traceless. And because the vectors they are rotating are real, SOD are real matrices, this makes B imaginary. So B is actually also a Hermitian matrix. Therefore the degrees of freedom of B is D squared minus D, because anti-symmetric matrices have no diagonal elements, and multiply by half, again due to anti-symmetry. Therefore the degrees of freedom of SOD is D times D minus 1 over 2. We have already derived this result in lecture 19. Therefore for SUN to represent d-dimensional rotations in the n-dimensional state space, this equation must be satisfied. That is, SUN must have the same number of generators as SOD. If we just take SU2 as an example in relation to SO3, setting n equals 2 and d equals 3 in the equation. This equation is satisfied perfectly. This is a beautiful result, since this means it is possible to rotate any state in the spin-half two-level state space into any other state in the same space. Why is this so? Because any normalized state can be transformed into any other normalized state by some unitary matrix in a given basis. For the spin-half two-level system, these unitary matrices must all be rotations, as we have just shown. But this is a special case. The equation must necessarily be violated if we still fix d to be 3, but consider higher spins. Now n is equal to 2j plus 1, with j larger than half. The right-hand side of this equation remains the same, but the left-hand side increases. This messes up our equation. But this is to be expected. If we are just counting rotations in an n-dimensional state space, n squared minus 1 is an overestimation, since not all SUN matrices represent rotations. And this number is the total number of generators of SUN. In other words, we may represent the d-dimensional rotation group with SUN, but it will contain more than just rotations. So the higher spin state space would contain unitary matrices that are not rotations, unlike the spin-half case. This equation helps us find the SUNs that exactly correspond to rotations and nothing else. The correspondence between SU2 and 3D rotations is a special case. The next simplest example is SU4, which represents 6D rotations. We can verify that the equation above is also satisfied for this case. Let's get back to our task of constructing higher spin states out of copies of spin halves. Earlier, we have figured out that the components of such a multi-copy state rotates like a tensor, with each index rotated by the matrix U. In our case, these are the 2x2 unitary matrices in the spin-half state space. The next question to ask is this an irreducible representation of rotations? In other words, would we be able to extract the j-multiplets out of state psi? To answer this question, let's first start with two copies of spin-half. It is a general fact that any two-index object can be written as the sum of two parts. One that is symmetric with respect to its indices, and the other anti-symmetric. It is easy to show that this symmetry or anti-symmetry remains unchanged by any linear, identical transformations on each individual index. For example, as represented by a matrix, the matrix U in our case, but this could in fact be any general linear operation as long as all the indices are acted on by the same matrices. To demonstrate that the transformed psi prime, preserves its original symmetry or anti-symmetry, let's switch the indices of psi prime. We can relabel the dummy indices, writing m bar as n bar and vice versa. Then switch the indices of psi using its symmetry or anti-symmetry. Notice that this expression is just the original psi prime before the switching of indices. Thus, we have shown that the symmetry or anti-symmetry of psi is preserved by identical rotations on each of its individual indices. This is an important result. This means that the symmetric parts rotates into symmetric parts, and anti-symmetric parts into anti-symmetric. The two don't mix. This is very similar to the fact that elements from different irreducible representations don't rotate into each other. In fact, later, we shall carry this decomposition to the fullest extent on more complicated multi-index tensors. Let's now look at this anti-symmetric component. This is an anti-symmetric 2x2 matrix in the spin-half basis, so it doesn't have any diagonal elements. And also, it has only one independent off-diagonal element, which we pick to be the up-down component. The sign and anti-symmetry is contained in this epsilon symbol, which is just the Levi-Civita symbol in 2 dimensions, as defined in the yellow box. All the diagonal elements are 0. The off-diagonal ones are opposite in sign. We can write psi A up-down in terms of its definition in the blue box below. This term in the bracket can be written concisely as the contraction between epsilon and psi. Thus, we have derived a projector that projects out the anti-symmetric part of a tensor. You can easily check that this would leave an anti-symmetric tensor unchanged. The anti-symmetric projector projects out only part of the information carried inside. Basically, it reduces a 2-index object into a no-index object. Less information because the sum over components always contain less information than all the individual components. And the epsilon symbol, which carries the free indices, doesn't really hold anything specific to psi. The rest of the information in psi is carried by the symmetric part. Let's consider something more general than this anti-symmetric contraction of psi. What about this object, which has some leftover indices after a contraction with epsilon? How does this transform under rotations? If we view the rotations of states as simply the transformation of the tensor psi to psi prime, then this n-2 index object is rotated simply by replacing psi with psi prime. The epsilon would then be transferred to the 2 U matrices attached to psi from the rotation. Let's look at this unit as a 2-index object with the free indices n1 and n2. Now we need to work out what this matrix is. Recall that the matrix U has determinant 1. We can use the Leibniz formula for determinants. This looks like the 1-2 element of our matrix. And with determinant 1, this is equal to 1. Since the epsilon symbol is anti-symmetric, our matrix is similarly anti-symmetric. This is similar to what we have worked out earlier. Let's see it again. Since our matrix is anti-symmetric and has an off-diagonal element equals to 1, this is exactly the description for the epsilon symbol itself. We can write this equation like so, taking the transpose of U's. And since U transpose also belongs to SU2, we can view this as the rotation of epsilon. And this says that epsilon is invariant under rotations. This is a very important result that will be used over and over again in this video. Thus this object we have defined transforms like an n-2 index tensor. So contracting a pair of indices of a tensor by the epsilon symbol just gives another tensor with two less indices. We can keep on applying these contractions to get tensors of lower ranks. This picture will come in handy later. Going back to the two-copy case, we see that psi can be separated into a symmetric tensor plus an invariant anti-symmetric tensor with a scalar coefficient. Scalar in this case just means some number that is invariant under rotation. We can apply this decomposition back to the state psi. Each of these terms have a definite symmetry. Let's consider them together. It is convenient to merge the two cats into one, just a change of notation. This is equal to the average. The two terms in the bracket is exactly equal. We have just labeled their dummy indices differently. Here's where we could use the symmetry or anti-symmetry of the tensor to exchange its indices. We could define this state in the red box as a new state that have definite symmetry or anti-symmetry under the exchange of particles. Of course, this state may not be normalized yet, but that's okay. For now, we are more interested in its symmetric properties. Let's apply this back to our decomposition. Now our state is in a basis that matches the symmetries of its tensor coefficients. This will allow us to refer to a tensor or its state interchangeably if they have a definite symmetry or anti-symmetry. Let's now examine the normalization of this new basis. Let's start with the state with both particles pointing up. This is already normalized if we assume that the spin-half basis is normalized. Similarly for both particles spinning down. There are two states with particles pointing in opposite directions, one symmetric and the other anti-symmetric. These are not normalized, since any state made up of an equal superposition of normalized states that are orthogonal to each other is normalized by 1 over the square root 2 and not half. Let's check. Let's denote these normalized states by a tilde. The symmetric and anti-symmetric states are also orthogonal to each other. This is clear from their definitions. Thus we now have an orthonormal basis with states of definite symmetries, or parity under particle exchange. Let's expand the state psi in terms of the new basis. Since both the coefficients and the basis have the same symmetry, these two terms in the symmetric part are actually equal. Similarly for the anti-symmetric part. The state psi is rotated by transforming its components by our earlier rule. The symmetry or anti-symmetry of the components are preserved by this rule. The rotated symmetric components are linear combinations of only the original symmetric components. Same for the anti-symmetric components. But since there is only one anti-symmetric component, and unitary transformation with determinant 1 for the case of just one component is just a trivial identity transformation. Therefore, psi a prime should be just the original psi a. This component is invariant under rotation. But let's verify this directly by looking at how this anti-symmetric state transforms. If it is invariant under rotation, so should be its coefficient, since after all, we have derived the transformation rule for the coefficients from how the states transform. Let's prove this. Let's rewrite this state as the following. This can be expressed as a contraction with the epsilon symbol. This is just a tensor attached to the basis states. But since the epsilon symbol is invariant under rotations, so is our state. Thus the symmetric part rotates into the symmetric part, while the anti-symmetric part is invariant. Let's put all these in a matrix form, starting with the symmetric part. Symmetric components are rotated into symmetric components by an unitary matrix. This is because an unitary transformation transforms an orthonormal basis into another orthonormal basis. This applies to our case. We could include the anti-symmetric part into this picture by extending the matrix. We can see from this picture that psi is actually a representation of rotations that is reducible into two separate blocks, the symmetric and anti-symmetric parts. Each forms a complete representation of rotations by themselves. This is a less trivial counterpart to the example we have made up earlier about two particles rotating on a 2D plane. We now look at states with symmetric tensors as their components. These tensors are totally symmetric between any pairs of indices. On the other hand, in the spin-half basis, there are only very limited number of tensors that could be totally anti-symmetric, because any component with repeated indices must necessarily be zero due to anti-symmetry. In fact, there is only one such tensor, the invariant epsilon tensor, which is associated with the anti-symmetric state we have derived for two copies of spin-half. All the other totally anti-symmetric tensors are just proportional to epsilon. This is why we focus on the symmetric case. As we have shown, this symmetry of the tensor is preserved by rotations. In fact, it is an irreducible representation of rotations. What we claim is that, for the number of indices n equals 2j, the states with totally symmetric tensors are just the states of the j-multiplet. To be more accurate, we are saying that they rotate in exactly the same way. Let's indicate the symmetry of these tensors explicitly, and write the product of the states in a more compact way. Again, let's try and find a set of basis states that matches the symmetry of their tensors with the help of the symmetric tensors themselves. First, we picked out any pair of indices. Notice that we can write this with the indices of the states switched without changing the result, due to the symmetry of the tensor. This allows us to take the average of the two. If we take this as the new state, it will be symmetric with respect to the two indices we have picked. But why stop with just symmetrizing two indices? The complete symmetry of the tensor allows us to take the sum of all the permutations of all the indices of the state, then just divide by the total number of permutation in an average. This way, we will have a basis that is completely symmetric, like the tensor it is attached to. We indicate this symmetrization by this bracket. Similar to the two-particle case, this basis may not be normalized, but different states are still orthogonal to each other. For example, for 3 spins. Due to the symmetry of the tensor, it is quite easy to list all its components. This simple counting shows that the tensor has only 2j plus 1 unique components. All the rest are equal to this set by permutations. Lo and behold, this number is exactly equal to the size of a j-multiplet. This is just a larger version of the symmetric part of the two-particle example from earlier. And in a similar manner, these components are rotated by unitary matrices that are 2j plus 1 by 2j plus 1 in size. Let me remind you what the unitary matrix rotating the components of the j-multiplet looks like. The relation between the Hilbert space operator rotating the states and the matrix rotating the components is clearly displayed here. Now for the symmetric states of 2j copies of spin half. The rotation operator is just the direct products of the operator rotating each individual copy. As we have shown, the associated matrix is also 2j plus 1 by 2j plus 1. There's a direct correspondence between these two representations. Let's look at the symmetric basis in details, specifically the state with all spin up. J3 of this state is just the sum of 2j spin up. This is just h bar times j. Exactly the quantum number for the highest weight state in the j-multiplet. Each spin we flip down corresponds to a change in the quantum number m by 1 unit, since we are dealing with spin halves. This is consistent with the smallest unit of separation between values of m. The same logic applies all the way to the lowest weight state with all spin down. This allows us to establish a one-to-one map between the symmetric multiple spin halves and the Jm states according to their J3 eigenvalues. This will also guarantee that all the rotation matrices of the two representations be equal, since all we need to know in order to calculate such matrices is how J3 acts on these states, as well as how J1 and J2 act in terms of the ladder operators. And these are completely determined by the rotation algebra, which is independent of representations. Thus, we have shown that the symmetric states of 2j copies of spin half is equivalent to the j-multiplet with regards to rotations. This is the tensor representation of spin j. But can we replicate the rules for the addition of angular momenta? Let's consider two spin states of spin j1 and spin j2, each composed of multiple copies of spin halves with totally symmetric tensors. What we meant by their addition is this. What angular momentum states can be constructed out of the product of these two bases? In general, states that are made up from the product of two totally symmetric bases have tensors which are symmetric within two sets of indices, each associated with either one of the bases. We have demonstrated this logic before. The states and tensors could be redefined to share the same symmetry. On the other hand, no particular symmetry is assumed for the exchanges of indices between the two sets. This is the most general case. This state is equivalent to a state that lives in the product space of two spin multiplets, J1 and J2, due to our earlier result. Our task now is to find all the irreducible representations in this product basis. These are the total spin multiplets. Let's focus on the tensor of this state. Let's try and express this in terms of irreducible representations. The way we do this is to use the decomposition formula from earlier. For a tensor with no particular symmetry between two of its indices, this allows us to write it as a sum of two components that do have definite symmetry and anti-symmetry. This works for any pair of indices in a multi-index tensor. We just have to apply this to our tensor above between its two sets of indices. We can continue to do this until each index on the left-hand side of the semicolon is paired with an index on the right, or vice versa, depending on which has more indices, until we run out of pairs. To make our job easier, let's simplify our notations. Symmetrization of two indices is represented by just a round bracket, while the anti-symmetrization is indicated by a square bracket. Let's apply the decomposition to the first index on either side, n1 and m1. We have written just the indices of the tensor, just to keep things tidy. Conventionally, this is how they are usually written. Partitions are used to separate out indices that are not symmetrized or anti-symmetrized within the brackets. Now we just keep applying the decomposition below to pair up the remaining indices between n and m. Now this is a key point. We apply the decomposition only to indices that have not been paired up yet. This way, the logic remains simple. We would not have to deal with complicated scenarios where one index could be in multiple pairs with different symmetries. To be specific, let's assume that J2 is greater than J1. That is, there are more m indices than n indices. This would not affect our general argument. Once we have run out of n to pair with m, the expansion looks like this, with a typical term like the one in the yellow box. Some pairs are symmetrized, while others anti-symmetrized. The remaining unpaired indices runs from m2j1 plus 1 to m2j2. The reason why we don't continue to apply the decomposition to indices on the same side is obvious. They are already symmetric with respect to each other, and so we couldn't split them up further using the formula below. Note that the anti-symmetrized pairs are now indices of the anti-symmetric tensor, epsilon, and are invariant under rotations. So only the symmetrized pairs of indices transform non-trivially under rotations. Let's look at this typical term more closely. It would be clearer for our discussion to group the symmetrized pairs and the leftover indices together, and the anti-symmetrized pair separately. As we have said, all the anti-symmetrized pairs are invariant and would not change under rotations, so we shall put our focus on the rest of the indices. We argue that all these are in fact completely symmetric with respect to each other. This is not so difficult to see once we take into considerations that m and n is symmetric among their own kind, while the symmetrizations pair every n with an m. We shall give a few examples, exchanging pairs of indices to show their symmetry. These should cover all the cases and prove our claim. We shall ignore the anti-symmetrised indices for now, since they are irrelevant to our discussion. Let's first express this in a form that will reveal the connections and symmetries between the indices more clearly. We shall represent the symmetrization between both sides of the semicolon by explicit connections like this, while remembering that the indices on the same side are symmetric with respect to each other. This is sort of like a symmetric bridge, which allows an index to cross over to the other side without changing the value of the tensor. Now let's begin our first example of switching indices. There are only two non-trivial cases. The first is exchanging a pair of indices that are on different sides of the semicolon but are not connected directly by a bridge. For example, n1 and m3. Using the symmetry between the indices on the same side, we can move m3 to the left, right next to the semicolon. Then switch m3 and n1 using this bridge. We can now move n1 to the right of m2 using the symmetry of the same side. This is where m3 used to be. Thus we have successfully switched the position of n1 and m3 without changing the value of the tensor. They are symmetric. The second non-trivial case also involves switching indices on different sides, but this time, one of them is one of the leftover indices that are not paired up. Let's exchange ni and m2j1 plus 1. We do this by moving m2j1 plus 1 into the position of mj using symmetry, then crossing the bridge to where ni is. Using symmetry on the same side again, we can move ni to the position where m2j1 plus 1 used to be. Thus we have shown that our tensor is symmetric with respect to the exchange of ni and m2j1 plus 1. These cover all the non-trivial exchanges that are possible between these indices, and they are all symmetric. With this typical index structure, after all the pairings for j2 greater than j1, we have just shown that all the indices are in fact totally symmetric with respect to each other. So this is the typical term we get by applying the decomposition formula below fully to our state tensor between the two sets of its indices n and m. Basically, we get a few pairs of indices and anti-symmetrize them, effectively transferring these indices onto the tensors epsilon, according to the rule in the green box. This will make them invariant under rotations. As for the remaining indices, they are symmetrized completely. But remember what we found out about totally symmetric tensors. They transform like spin multiplets with definite values of the quantum number j. Keep this thought in mind as we give a more explicit demonstration. We shall now go through the terms that result from applying the decomposition expansion one by one. Let's start with the term where there are no anti-symmetric pair. This is the completely symmetric term. So we have a symmetric tensor with 2 times j1 plus j2 indices. As we have shown earlier, the components of this tensor corresponds to the spin j1 plus j2 multiplet. This is exactly one of the total angular momentum multiplets that could arise from the composition of j1 and j2. Let's see if we could derive all the other multiplets that we have shown in lecture 21, which could result from such a composition. The next possible tensor would include one anti-symmetrised pair with the rest of the indices completely symmetrised. More explicitly, this corresponds to the tensor where two indices of psi are eaten up by the anti-symmetric projector and transferred onto the invariant epsilon symbol. The rest of the indices belongs to a totally symmetric tensor with two j1 plus j2 minus 2 indices. Let's drop the half in front because it is irrelevant to our discussion. This tensor in the blue box belongs to the spin j1 plus j2 minus 1 multiplet. This is the first of a series of lower-rank symmetric tensors that Weinberg referred to in his book, which represent the irreducible representations that could result from combining two spins. Note that there are also other terms with similar index structure, where it is the other pairs that are anti-symmetrised. But they give identical results when contracted with their basis states, because the indices n and m are symmetric within their own set, so are the basis states. They are in fact the same term, just summed over in a redundant way over symmetric indices, then divided by all these permutations. For the next term in our tensor decomposition, we have one more anti-symmetrised pair. Where the tensor in the blue box gets reduced by two more indices by contraction with epsilon, these are transferred to another epsilon and become invariant under rotations. The rest of the indices are symmetrised as usual. With each contraction, the spin of the representation gets reduced by 1. We can continue with this process, contracting with epsilons on one end and spitting out invariant tensors on the other, until all pairs become anti-symmetrised. The number of symmetrised indices left is just 2j2 minus 2j1 plus 1 plus 1. Which is 2 times j2 minus j1. And given our assumption of j2 greater or equals to j1, this is just equal to 2 times the absolute difference between j2 and j1, which corresponds to the spin equals to the absolute difference between j2 and j1. This is exactly the lower spin that could have come from the composition of j1 and j2. We have derived this in a different way in lecture 21. As mentioned before, no further contraction with epsilon is possible with the remaining indices, as they are all symmetric and would just give 0. Starting with a tensor with 2 times j1 plus j2 indices, we have generated a series of tensors with lower ranks. That corresponds to multiplets of spin equals j1 plus j2 down to their absolute difference in intervals of 1. All these states do not mix under rotations, because they have tensors with different combinations of symmetric and anti-symmetric indices. This is exactly what we would expect for representations with different spins. Thus, we have successfully derived the rules for the addition of angular momenta, as discussed in lecture 21, using the tensor representation of rotations. it would be instructive to study the special case where j1 equals j2. This corresponds to the case of two identical particles. By particles we mean the copies of spin halves that made j1, which is considered as one particle, while all the other spin halves that made up j2 as another. This corresponds to the following state. As we have said, one group of spin halves made up particle 1 and the other group particle 2. They both have the same spin of j1. Let's see what happens when we exchange the two particles. By this we mean exchanging the states of the two identical particles. Of course, such an operation is only possible if the two particles are identical and can have access to the same states. This is also equivalent to exchanging their tensor indices. Let's start with the state with the totally symmetrised tensor. This corresponds to the largest spin from the composition, spin 2j1. Exchanging the particles gives. Due to the symmetry of the tensor, we can switch its indices while maintaining equality. Now we change the dummy indices for summation. And we end up with the original state. This shows that the spin 2j1 multiplet is symmetric under particle exchange. Let's note down the dimensionality of this multiplet, as well as its symmetry. The next state in the composition has one epsilon contraction and is effectively equivalent to the following symmetric tensor under rotations. This corresponds to the previous spin reduced by 1. This tensor has an index structure of one pair of anti-symmetric indices, with the rest totally symmetric. It is not difficult to see that this epsilon will make the entire state anti-symmetric under particle exchange. Let's check. This is the exchange state. Then we make the following change of dummy indices. Now using the anti-symmetry of epsilon, we get a minus sign. Here we do another change of indices. At this point, we can make use of the symmetry of these indices to switch n and m. Notice that the state in the blue box is just the original state. This means our state is anti-symmetric under particle exchange, just as expected with one epsilon. Once again, let's note down the dimensionality and the parity of the exchange, this time anti-symmetric. Here we introduce the direct sum symbol. This is what we use to collect together the independent representations that can result from our composition. One could see this sum as the sum that appears in the decomposition formula of symmetric and anti-symmetric components. Next, we move on to states with two epsilons. Two epsilons will give us two minus signs under particle exchange, while the symmetric indices are unaffected. This gives a state that is symmetric under exchange. 3 epsilons will give us another anti-symmetric multiplet under particle exchange, and so on and so forth. This pattern continues until we reach spin 0, which has only one state. The tensor of this state is effectively just a scalar, with no free indices, while its original indices are now carried by epsilon tensors, making the state invariant under rotations. To find out whether a state is symmetric or anti-symmetric under exchange of particles, just count the number of epsilons. There are two J1 epsilons for this state, each giving one minus sign under exchange. For even powers, the state is symmetric with J1 equals an integer. For odd powers, it is anti-symmetric with J1 equals half integer. Let's look at the simplest example of J1 equals half. This is the case where the spin 0 state is anti-symmetric under particle exchange. And we have one index on either side of the semicolon. The highest spin is 1, which has 3 basis states that are all symmetric under particle exchange. So the product of two spin halves will give us a spin 0 and a spin 1 representation. This just corresponds to our decomposition formula. Let's see the associated states again. This is our earlier result. The triplet of states that are symmetric under particle exchange belongs to the spin 1 multiplet, while the anti-symmetric state is the spin 0 singlet. We remind you below how the composite states of opposite spins are defined. Let's do one more example. J1 equals to 1. Psi has two indices on either side of the semicolon. This is the product of two spin 1 multiplets. We can read this off the general result in the red box directly. So we have a spin 2 multiplet with 5 symmetric states, a spin 1 multiplet with 3 anti-symmetric states, and a spin 0 singlet that is symmetric. This equation is a key result regarding particles with identical spins. You may have noticed that for a given spin, we can have states that are both symmetric and anti-symmetric under particle exchange. If you have taken some statistical mechanics, then you must be aware that in quantum mechanics, a particle must satisfy definite statistics. It could either be a boson or a fermion, depending on its spin. If it's a boson, then it must be symmetric under particle exchange, while if it's a fermion, then anti-symmetric. The result above seems to contradict this, so what's going on? The answer is that we have up till now been considering only the spin states of a particle, while the quantum statistics applies to the entire state, including the orbital states of the particle. These describe the particle's position or motion. Only the entire particle state has a definite symmetry or anti-symmetry under particle exchange. The result above will be useful in the construction of such states later on in this chapter. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.